If you define the Big Bang really carefully as the time when the universe was very hot and very dense.
As star's survival seems beyond the realm of science fiction, this week astronomers shuttered our universe's most deadly predator.
In our skies just got stranger. Howard's top scientists saying it could be a nuclear-powered alien craft.
Have you ever looked up at the night sky and wondered, if the universe is so vast, why haven't we met any aliens? Billions of stars, countless planets, yet not a single confirmed sign of intelligent life. Where is everybody? Or consider this, what if the reality you think you know isn't really what it seems? What if time doesn't flow the way you feel it does? Or a cat could be both alive and dead at the same time? Today, we're diving headfirst into some of the most mind-bending paradoxes in science and philosophy. These are the puzzles that have kept the brightest minds awake at night, challenging everything we think we understand about the universe. From the mystery of silent civilizations across the cosmos, to the strange and counterintuitive world of quantum mechanics, to the secrets locked inside black holes, and even the strange ways time can stretch and bend, each paradox forces us to question our assumptions, our intuition, and the very nature of reality itself. By the end of this journey, you might start to see the universe and your place in it through an entirely new lens. So tell me, which of these paradoxes do you think is the most unsettling? Is it the possibility that we're alone in the universe, or that reality is far stranger than our minds can grasp? Keep that question in mind, because we're about to explore the answers, or at least the mysteries. A paradox is one of the most fascinating puzzles in science and philosophy. It's a situation where logic and reality collide, where what seems obvious just isn't. On the surface, a paradox feels like a contradiction, but dig a little deeper, and it often reveals profound truths about the universe. Paradoxes force us to confront the limits of our understanding, showing us that nature doesn't always follow the rules our intuition expects. Scientists and philosophers are drawn to paradoxes because they expose gaps in our knowledge, spark creative thinking, and push the boundaries of theory. Some paradoxes are resolved over time, like the famous twin paradox in relativity, while others continue to challenge our deepest assumptions, like the mysteries of black holes and quantum mechanics. In many ways, paradoxes are the compass guiding us toward the unknown. Today, we'll explore 4 of the most mind-bending paradoxes that have kept scientists awake for decades. First, the Fermi paradox asks why, if the universe is so vast, we haven't seen any signs of intelligent life. Then we'll enter the bizarre world of Schrödinger's cat, where quantum mechanics suggests reality itself can be in 2 states at once. Next, the black hole information paradox questions whether information can ever truly be lost in the universe. Finally, the twin paradox challenges everything we think we know about time itself. Each of these paradoxes is a window into the strange, counterintuitive, and often unsettling truths of our universe. As we go deeper, prepare to have your mind stretched and your assumptions questioned. Where is everybody? In the vast expanse of the universe, there are more stars than grains of sand on all the beaches of Earth. Many of these stars host planets, and some of those planets could, in theory, support life. So, if the cosmos is so enormous and life emerged here on Earth, why haven't we encountered any other intelligent civilizations? This question was famously summed up by Carl Sagan when he asked, "Where is everybody?" It is a puzzle that continues to haunt astronomers, biologists, and philosophers alike. We look at the night sky and wonder not just about the stars themselves, but about the possibility of neighbors we have yet to meet, and the silence is deafening. The Fermi paradox captures this profound tension between expectation and observation, a mystery that challenges our understanding of life in the universe. The paradox becomes even more striking when we consider the numbers. Our galaxy, the Milky Way, contains roughly 100 to 400 billion stars, and recent astronomical surveys suggest that a large fraction of these stars host planets. Many of these planets lie in the so-called habitable zone, where conditions might allow liquid water to exist, one of the key ingredients for life as we know it. Earth itself is proof that life can emerge under the right conditions, and it appeared relatively quickly on a cosmic timescale. By probability alone, intelligent life should be common. Yet, despite decades of searching, there is no unambiguous evidence of extraterrestrial civilizations. No radio signals, no interstellar probes, no contact. This discrepancy between the high probability of life and the absence of any signs is exactly what makes the Fermi paradox so unsettling. Scientists have proposed several explanations, each offering a potential way to resolve this cosmic mystery. One possibility is the rare Earth hypothesis, which suggests that the combination of factors required for complex life is extraordinarily uncommon. Maybe Earth-like planets with the right atmosphere, stable climates, and protective magnetic fields are far rarer than we imagine. Another theory is that intelligent civilizations tend to self-destruct before they can spread across the stars, falling victim to nuclear war, ecological collapse, or technological disasters. Some scientists speculate that advanced civilizations may deliberately remain silent, either to avoid detection by hostile species or because they follow a cosmic prime directive, a concept known as the zoo hypothesis. A more philosophical twist is the dark forest theory, which proposes that the universe is a dangerous place, and silence is the safest survival strategy. Finally, it is possible that extraterrestrial life is abundant, but we simply lack the technology or understanding to detect it. Our current instruments may be too primitive, and our assumptions about communication too narrow to recognize alien signals. As we consider these possibilities, the Fermi paradox becomes more than a scientific puzzle. It becomes a mirror reflecting our own assumptions about life and intelligence. Are we really as special as we think, or are we just a fleeting spark in a vast, silent cosmos? Could other civilizations be watching us without revealing themselves, or is humanity truly alone in the Milky Way? The paradox challenges our imagination, forcing us to consider not only the likelihood of alien life, but also the reasons for its apparent absence. It is a question that combines astronomy, biology, and philosophy, blending hard science with the deepest mysteries of existence. So, what do you think? Which explanation seems most likely? Are we alone, or is the universe teeming with life that deliberately avoids us? Perhaps the silence is not evidence of absence, but of caution, or maybe it reflects our own limits in perception and understanding. Whatever the answer, the Fermi paradox invites us to look up at the stars with wonder and humility, reminding us that the universe is far larger and far stranger than we can easily comprehend. Take a moment to imagine the possibilities and share your thoughts. Are we truly alone, or is someone or something watching silently from the dark reaches of space? The quantum oddity. The paradox arises because, at the quantum level, particles do not have definite states until they are measured. In the world we experience daily, things are either one way or another. Yet, in the microscopic domain, such superpositions are normal. Does reality exist independently of observation, or is it shaped fundamentally by the act of measurement? The implications of this paradox ripple far beyond a single thought experiment. It exposes the role of the observer in quantum mechanics, a question that has puzzled physicists for nearly a century. Different interpretations attempt to make sense of the scenario. The Copenhagen interpretation suggests that reality is not definite until measured. The many worlds interpretation, on the other hand, proposes that both outcomes occur, but in separate, branching universes. Objective collapse theories suggest that quantum superpositions have a natural limit, and at some scale, they collapse spontaneously without observation. The principles of superposition and measurement are at the heart of quantum computing, where qubits can exist in multiple states simultaneously, allowing for vastly more powerful computation than classical computers. Quantum cryptography relies on similar principles, using the behavior of quantum particles to secure information in ways that are theoretically unbreakable. Understanding and experimenting with superposition is no longer just a thought experiment, it is shaping the technology of the future. So, what does this mean for reality itself? Is the universe fundamentally probabilistic, with outcomes only solidifying when observed? It forces us to consider the possibility that our perception of reality is inseparable from the act of observation, challenging everything we think we know about existence. Universe's biggest secret. Black holes are some of the most mysterious objects in the universe. These cosmic vacuum cleaners are so dense that not even light can escape their grasp. Anything that crosses their event horizon, the invisible boundary around a black hole, is thought to be lost forever. For decades, black holes were considered the ultimate prisons of the universe, devouring matter, energy, and information without a trace. Then, in the 1970s, Stephen Hawking made a shocking discovery. He showed that black holes are not entirely black, they emit a faint radiation, now known as Hawking radiation, and over time, this radiation can cause a black hole to evaporate completely. While this was a groundbreaking insight, it also opened the door to a profound paradox. The paradox arises when we consider what happens to the information about everything that falls into a black hole. According to general relativity, anything that enters a black hole is trapped forever, and if the black hole eventually evaporates, that information appears to vanish from the universe. But quantum mechanics insists that information can never be destroyed. The laws of physics are fundamentally unitary, meaning the quantum state of a system should, in principle, be reversible. This clash between general relativity and quantum mechanics raises an unsettling question. If information is truly lost in a black hole, then the universe itself could be unpredictable at a fundamental level. Determinism, the idea that the past can always inform the future, would break down, and if information cannot be lost, then somehow it must escape or be preserved in a way we do not yet understand. Several intriguing proposals attempt to resolve this paradox. One is the holographic principle, which suggests that all the information about the three-dimensional objects that fall into a black hole is actually encoded on its two-dimensional surface, the event horizon. In this view, the universe behaves like a hologram, where the true information is stored at the boundary, not inside. Another idea is black hole complementarity, which posits that from the perspective of an outside observer, information is never lost, but is instead smeared across the event horizon, while from the perspective of someone falling into the black hole, they experience a different reality. String theory offers another perspective with the fuzzball proposal, which replaces the classical notion of a smooth black hole with a tangled, stringy structure in which information is never truly trapped. While these ideas are promising, none have been universally accepted, and no experiment can yet confirm which, if any, is correct. The black hole information paradox forces us to confront questions that go beyond physics. Could the universe itself be a hologram? Are there hidden layers of reality that encode information we cannot perceive? If information can be preserved in ways that defy our current understanding, it suggests that reality is far stranger and more complex than our everyday experience allows. Thinking about black holes is not just an abstract exercise, it challenges the very principles of causality, determinism, and the nature of the universe itself. For scientists, philosophers, and curious minds alike, this paradox is a reminder that the universe still holds secrets beyond our comprehension. Now take a moment to imagine standing at the edge of a black hole. Everything you know about space, time, and information is suddenly upended. Could the entire cosmos operate like a hologram, with hidden layers encoding every particle and event? What would it mean for our understanding of reality if information can never truly disappear, even from the most extreme places in the universe? The black hole information paradox invites us to stretch our imagination and question the foundations of physics, offering a glimpse into a universe far stranger than we ever expected. Twin paradox. Imagine two twins. One stays on Earth, living a normal life, while the other boards a spaceship capable of traveling near the speed of light. After years of journeying through the cosmos at unimaginable speeds, the traveling twin returns home. Which twin will be older? It seems like a simple question, Yet the answer defies common sense. In the world of relativity, time is not the universal constant we experience every day. This thought experiment, known as the twin paradox, has fascinated scientists and philosophers alike, revealing that time itself is far stranger than our intuition suggests. At first glance, the paradox appears symmetrical. From the perspective of the traveling twin, it could be argued that the Earth itself is moving, suggesting that the Earth-bound twin should age less. Yet, when they reunite, the twin who journeyed at near light speed is objectively younger. This outcome is a consequence of time dilation, a fundamental prediction of Einstein's theory of special relativity. As objects move closer to the speed of light, time for them slows relative to stationary observers. Combined with the relativity of simultaneity, which states that different observers can disagree on the timing of events, the twin paradox shatters our everyday assumption that time passes equally for everyone. The resolution lies in the asymmetry of the situation. The traveling twin experiences acceleration when turning around to return to Earth, moving from one inertial frame to another. This acceleration breaks the apparent symmetry between the twins, making the two journeys fundamentally different. The Earth-bound twin remains in a single inertial frame, while the traveler switches frames, causing less time to elapse for them. Space-time diagrams provide a visual way to understand this. The traveling twin's path through space-time is shorter, and time along their trajectory passes more slowly. The paradox is not a flaw in relativity, but a striking illustration that time is flexible, shaped by motion and gravity. It forces us to abandon the comforting notion of absolute, universal time and embrace a universe where time can stretch, compress, and behave in ways that feel completely alien to everyday life. Why paradoxes matter? Paradoxes are more than intellectual puzzles or thought experiments. They are windows into the limitations of human understanding. Each paradox we have explored reveals the boundaries where our theories, observations, and intuitions clash with the deeper workings of reality. The Fermi paradox challenges our assumptions about life and intelligence in the universe, asking why we have yet to encounter other civilizations despite overwhelming odds. Schrödinger's cat exposes the strangeness of quantum mechanics, showing that reality at its smallest scales behaves in ways that defy common sense. The black hole information paradox highlights unresolved conflicts between general relativity and quantum mechanics, forcing us to confront the possibility that even fundamental principles like information conservation might be more subtle than we imagine. The twin paradox demonstrates that time itself is not absolute, revealing a universe where even familiar concepts like age and duration are flexible and observer-dependent. These paradoxes matter because they do not just highlight contradictions, they expose gaps in our understanding and drive scientific progress. The twin paradox, for example, is well resolved within the framework of relativity, yet it still challenges our intuitive sense of time. The black hole information paradox, on the other hand, remains an active area of research, motivating efforts to reconcile quantum mechanics with gravity through ideas like the holographic principle, black hole complementarity, or string theory. Even the Fermi paradox, which depends heavily on assumptions about life and detectability, forces us to confront profound questions about our place in the cosmos. Paradoxes compel us to rethink our assumptions, confront the unexpected, and expand the limits of what we consider possible. Ultimately, paradoxes remind us that nature may be far stranger than we imagine. They challenge the comforting idea that the universe is simple, predictable, or fully comprehensible. By confronting these paradoxes, we are forced to ask profound questions. What do these mysteries tell us about reality, about life, and about the universe itself? How much of what we perceive is shaped by our assumptions, and how much remains hidden, waiting to be discovered? Now it's your turn. Which paradox blows your mind the most? Is it the silence of the cosmos in the Fermi paradox, the dual life of Schrödinger's cat, the secrets hidden inside black holes, or the mind-bending time of the twin paradox? Share your thoughts in the comments below. I want to hear your theories, questions, or even wild speculations. If today's video left you curious, there's a whole universe of mind-bending content waiting. Check out our videos on quantum mysteries, the strangest phenomena in space, or other time paradoxes that defy everyday logic. Remember, curiosity is the first step toward understanding, and the universe is far more astonishing than we often imagine. Thanks for joining us on this journey through the weirdest, most fascinating paradoxes science has to offer. Don't forget to like, subscribe, and hit the notification bell so you never miss an adventure in